Hello, chemistry class. Here we are again. We're going to jump into chapter 19 today. I'm going to do kind of a quick overview of this chapter. You'll find here as we are talking about materials chemistry that it's just a lot of descriptive stuff here. Hopefully you'll enjoy some of the discussion of the development of various materials and how chemistry has improved our lives through research done in these fields. Some of you might one day be involved in developing new materials just like these. So let's jump into this together. So chapter 19A is on ceramics. Ceramics are non-metallic inorganic solids formed by shaping and firing a mixture until it hardens. Although they may be formed from a wide range of compounds, most ceramics are crystalline, which means that they have a lattice structure, right? So traditional ceramics would include even things like pottery and artwork made of clay and other materials. Ceramics have been around for a very long time. We even find in a lot of archaeological digs, they find a lot of pottery. Pottery has been around for a long time. Traditional ceramics were shaped and fired in kilns. And as I mentioned here already, they were known in ancient times. But there's a huge field today in advanced ceramics. Now, there are a few different major types of these. First of all, the oxides are ceramics that are chemically inert, which means in general they don't engage in chemical reactions. They are electrical insulators, and they are low on the scale range of thermal conductivity. So they insulate against electricity and against heat. Aluminum and zirconium oxides are among the most prevalent. You then also have non-oxides, which are extremely hard conductors of heat and electricity, things like carbides and nitrides. And lastly, you have composites, which are very lightweight and shock resistant. Advanced ceramics you find in all kinds of applications today. So advanced ceramics, well, traditional ceramics, you just had like a shaping and then you would put it into a kiln, like a big oven, right? And you'd fire it until it hardened. The process for advanced ceramics is most of them go through what's called the sol-gel process, where they'll grind it to fineness. They'll then add water and form it to shape, and then they fire it to harden it, called sintering, and then they finish cut it to size. Ceramics can be found in cars, electronics, homes, and the health industry. If you look at page 502 and 503 in your chemistry books, you will see a great discussion of the various ways in which ceramics are used in industry today. Everything from light bulb sockets to lining metal vats and pipes that are carrying molten metal. They're used in applications in cars. There's ceramic vibration sensors that are used in cars' computer systems. They're all over the place. They're also used in homes. Everything from in floor tiles and wall tiles to ceramic plates, filter material. It's used in paint texture, used in alarm systems. So lots and lots of different ways which they're used. Also used in cell phones, and even in the health industry today, and in particular the dental industry. So ceramics are all over the place. All right, so section B then is on semiconductors. Just a few words to say about this. What makes a semiconductor? Well, a conductor is usually made of a metal where electrons can move freely and transfer a current, whereas insulators are usually nonmetals, and they oppose the flow of current. We call these resistors. So a semiconductor has varying degrees of the characteristics of both metals and nonmetals. And as a result, we're not all that surprised to find them on the periodic table in between, kind of separating the metals and nonmetals. If you'll remember from the periodic table, it's kind of like a green line on a stair step. That is the range of semiconductors. So there's some types of semiconductors to just be noted. There's first the N-type semiconductor, which has an extra valence electron, and the P-type semiconductor, which is usually missing a valence electron. So There's the N-type, which has extra electron present, and the P-type, which has missing electrons. As I said a moment ago, if you remember from the periodic table, here is the kind of stair step of the semiconductors, silicon being one of the most important of these, but they will also utilize, as you have here, boron, aluminum, and gallium are utilized as p-type semiconductors, where they need to promote a hole in the lattice structure. They're using something with, remember, this would have like 3 valence electrons versus the 4 of like silicon or germanium. If you're doing an n-type semiconductor, or you're using phosphorus, antimony, arsenic, notice that those are right here, phosphorus, arsenic, and antimony. You'd add these to a silicon lattice or wafer in order to produce an n-type semiconductor. So your p-type semiconductors would be here. Your n-type semiconductors are making use of these, and they would be grafted in order to introduce either an extra electron or a lack of an electron. Now, why would you want to do that? Well, this is how semiconductors are used. They act as switches and electrical components. And you've maybe heard of transistors and integrated circuits before, but there's a couple of pictures in your book on page 506 that shows what this kind of looks like. Note here in this diagram, you have an N-doped semiconductor here that's sitting on a P-doped semiconductor here. And in this case, we have the FET is on, current is flowing through here because there's no voltage being applied to this N-doped semiconductor. But over here, the FET is off, no current is flowing because there's a positive voltage being applied here to the N-doped one, which has caused a depletion region, and it's closing the channel, preventing current from flowing through the P-doped semiconductor. So this just gives you a quick example. There's a lot of science and technology behind how semiconductors work, but just to give you an idea, there's currents and voltages that are being applied at various places, and they can turn on or off switches through this method. This brings us to section C. I told you this would go pretty quick today. Discussion of polymers. So polymers are large units formed by linking many repeating units called monomers. So a polymer is a large unit formed by linking many monomers. Mono meaning one, poly meaning many. So it's the grouping of many members, polymers, of single members, monomers. Copolymers are whenever you have a polymer that is built from 2 or more different monomers. So if you had one monomer named A and another one B, and you just started linking these like this, A, B, A, B, A, B, and on it goes, that would be a copolymer because your monomers are 2 different things that are being joined together. Now, in addition, polymers form by breaking double bonds in order to bond monomers together. Polyethylene can take many different forms, but this is just an example of that. Here's your ethylene molecule, which you learned about last week as we talked about organic chemistry. But note here, this carbon, there's a carbon here and a carbon here, and they're joined by a double bond, leaving then 4 hydrogens on the outside. And so what happens with polyethylene, ethylene is the monomer, polyethylene is what we're building. We build that by taking many ethylene molecules and breaking this double bond that's in between each of these carbons and splitting it apart into a single bond so that way it can be joined together with other ethylene molecules until it looks like this. Now, polyethylene, which is very, very prevalent as a polymer, can take on various forms. First of all, there's high-density polyethylene, which is used to form rigid, useful products from everything from kayaks to bottles. This is usually very rigid applications. Whereas low-density polyethylene is something you would find in like grocery store bags. Whereas cross-linked polymer, polyethylene, has side chains that link the strands together, and this is stuff that's used for extremely rigid applications like pipes. So I kind of picture each of these up here in the top right corner, and which one of these do you think is the low-density polyethylene? Or maybe we should start with the cross-linked. Which one do you think is cross-linked? That one probably stands out the most. Yeah, it's this one. The blue one is the cross-linked one because you see these little linkages that are between each of these strands. Which one do you think is low density? Well, the answer is this one. The red one is actually the low density polyethylene. These little branches that are sticking off from here prevent these from laying down flat and right next to each other. So it kind of causes them to sit off of one another, making it lower density. And this guy that has nothing out from the sides is able to lay down much more flat. This is high density polyethylene. Okay, then you have, besides polyethylene, you have polystyrene. And by the way, polystyrene can come in both foam and clear drinking cups. So both the clear plastic cup that you might drink from, that's polystyrene, as well as the foam cup that we're used to for like drinking like hot cocoa or coffee. That's also polystyrene. And it looks like this. There are many styrene molecules that are joined together. Again, you have a double bond here that splits apart in order to then link them together into many, many groups of styrene molecules. Therefore, it's called polystyrene. And then you have polyisoprene, also known as rubber. It's most useful after vulcanization, which was a process that was discovered by a chemist. You can actually look that up on YouTube. There's some really fascinating videos that have been done on the history of rubber. And really, I say fascinating. You're like, oh, I don't think it would be fascinating to me. I think you would find it fascinating. You can look into this really interesting history surrounding rubber. But what they discovered is that rubber becomes much more useful when it's heated with sulfur, because then it forms a lot of cross links and becomes a lot more durable. So there's natural rubber that comes out of a rubber tree, only grown in certain areas of the world, only places where it grows well. And then again, there's a very sordid history regarding that, and some horrible things that happened to native peoples as a result of economic demand for further rubber. But there have then been synthetic forms of rubber that are produced today also through chemistry. And then you have condensation polymers. So those are all addition polymers. These are condensation polymers, which when they combine, they release water. That's why they're called condensation polymers, because when they form together, there's a condensation reaction, water is released. Often they're made with alternating monomers, and one of the most famous of this is nylon. And if we were in class together, this is one of those demonstrations I like to show you. You take hexadiamine right here, it's pictured here, and then you take this adipic acid, and when you put the two things together, you can put them together just into a beaker, and then right where the two chemicals meet, you'll see a little fine kind of layer, almost looks like a little skin, and you can take a paper clip and just grab at that little skin and pull up, and then continue to pull up, and as you pull up, you continue to form more and more nylon into a long string, just coil it up on itself. Nylon is the combination of diamine and dicarboxylic acid, and that's how then it forms. So you notice here that when you form this, you also get water. That's why it's called a condensation polymer. Polyester is another condensation polymer. So nylon and polyester, we are familiar with that in clothing.
Well,
is this sort of how they make nylon?
That's exactly how
it's
they make
how it's done. Yeah, wherever the point of contact with the two chemicals.
Whoa.
If you look at the nylon
It's
itself,
so thin.
well, if you look at the nylon itself, look how it actually has like smoke, not the smoke,
Yeah.
but it's the,
steam or whatever.
yeah.
Gas.
Fumes.
What do they use?
So what do we have? Oh.
How do the workers?
They probably
It's
have
probably
machines.
Well, they have like
Machine.
Yeah, you don't have to have a
machines
person sitting doing this number.
and stuff. Oh my god.
Yeah, what's your job?
Forever.
Nylon twister,
The
Twirl.
nylon
We get paid
fabrication.
In China,
twirling.
in China
We
they
get
might
paid
have
a lot because we die at around 30 years old.
In China, they might have people doing stuff like this because they do a lot of this
You guys
stuff
notice
by hand.
notice that this whole thing is all one
Is it a straight?
one molecule, right?
Yeah.
What we're doing here, this is all one molecule, all
Oh,
connected
Jesus,
together.
it smells.
Jeez.
Oh,
There it goes.
That's one molecule? Wait.
One
Oh my
molecule
God.
right there. You feel the weight on
Is
that.
it heavy?
Now again, it's like one of those things where, depending on what's left in there,
Yeah.
it might have been not.
Now, plastics are polymers that can be formed into different shapes, normally when heated or pressurized. Elastomers exhibit rubbery or elastic behavior after formation. Thermoplastics can be reheated, reshaped, and reused, whereas thermosets are difficult or impossible to melt and reshape. So if it's a thermoplastic, you can melt it down again and reshape it and reuse it, whereas a thermoset is something where it's almost impossible to melt it down and reshape again. So thermoplastics are those which are most readily able to be recycled, whereas thermosets, usually we have to, if we're going to not just let them sit into a landfill, we need to find another use for them. So sometimes, for example, they'll use thermosets in applications like a material that can be placed out as like on a playground material surface or something of this nature, where you don't really have the opportunity to just reshape it in whatever you want, but you could still maybe use it for some other application. Now, most plastics are not biodegradable. Recycling is a wise choice for some plastics, though. And there are seven categories or codes for plastics. They must be sorted and cleaned. Only about 5% of plastic products actually, though, get recycled every year. And you've maybe seen this before. This is another exercise you can do on your own. You can go through your house and look at plastic bottles and look on the bottom of those bottles, and you will see a recycling number associated. And each of these numbers is associated then with a different thing. So number 1 is polyethylene. In general, you see the general density that is given for that. You then have high density polyethylene, HDPE is number 2. PVC or polyvinyl chloride is number 3. Low density polyethylene is number 4. Number 5 is polypropylene. Number 6 is polystyrene. And then 7 is the number that's used for a lot of other things, including polycarbonate, nylon, and acrylics. So those codes are on the bottom of these different bottles, and you'll be fascinated to find all kinds of different codes on different pieces of plastic. This would be actually a good exercise. See if you can find all 7 different recycling numbers in your house. Maybe get your family to tag along for this little exercise, but look through your house and see if you can find all 7 different recycling numbers. All right, then you have biopolymers, which are a increasing field today. PHA, PLA, and TPS, these are all described in your book. They are biodegradable, and they are usually formed from plant fibers. So the idea is if we could go into more and more biopolymers, then whenever they're thrown away, they would biodegrade instead of just sitting there forever and filling up landfills. Which brings us to our last section in Chapter 19 on nanotechnology. Nanotechnology is the branch of science that combines the disciplines of chemistry, engineering, and materials science to manipulate atomic or molecular substances for the purpose of creating useful products to benefit mankind. There's your official definition. So nanotechnology involves manipulating atoms or molecules one at a time to construct useful objects. This is very literally engineering from the bottom up. You're going to take the smallest little particles, little atoms, and forming something out of that. These are using molecules between 1 and 100 nanometers, which in general deals mostly with carbon, but also silicon and fullerenes are carbon molecules arranged either as a sphere or a cylinder or a tube. Buckyballs are probably the most famous example of fullerenes. These are carbon balls shaped like soccer balls. They're called C60 because there's 60 carbon atoms that are utilized in this. And it looks like a geodesic dome, almost like the Epcot Center, right, in Disney World. They can form naturally in candle soot, and they are part of the class called fullerenes. And then you have carbon nanotubes, which can be single-walled or multi-walled. They usually amount to about 1 nanometer in diameter. And they can be used for batteries, display screens, targeted medical treatments, or super strong materials like orbital tethers. Again, your book has some interesting discussion about these matters. Nanotechnology could help reduce the use of fossil fuels and make breakthroughs in other scientific fields, but implications of nanotechnology are still unknown. This is a discussion of nanotoxicity. There hasn't been a lot of study done yet on what could be the potential environmental implications of nanotechnology being used more and more. Because these things are so very small, they can move in and out, for example, through skin membranes without the skin being able to protect you. And so the question is, could this cause any contagions or problems for health? A lot of those questions are still on the table being discussed and studied. Nano-sized particles can often exhibit different characteristics than they do on the macro scale. So even things that might be safe on the macro scale might not be so safe on the micro scale or the nano scale. The nanotechnology revolution could be as transformational in this century, though, as the technological revolution was in the last century. And so it is certainly an area of chemistry that is expanding and growing. Well, I've just taken us through chapter 19. It's a pretty quick chapter. I'm asking you guys this week to work on the odd numbered problems for all of the section reviews. So A, B, C, and D. There's not that many questions involved there, but you look through those questions. I've provided you with the answers to those, so make sure you work on those this week. There is no test this week. I hope that you guys do enjoy Good Friday and Resurrection Sunday. I know things are a little bit different with COVID and everything that's going on. So I'll be praying for you guys. Please do stay safe and shine as lights in this world. It's a world that's in darkness and needs to know Christ. Let's pray that even these situations would cause men to call upon Jesus to save them. God bless you guys. Have a wonderful week. Bye-bye.